A relation is a rule that connects two sets of objects, x and y. I use x and y, but it doesn't have to be numbers. It could be things, and you'll encounter some of these as you work through the exercises. So you should have your rubric handy. This box here contains your vocabulary. This here, 7 different ways to represent a relation, and of course this is your self-check. Here's an example of a relation in sentence form. The diameter of a circle is twice radius. So the diameter of a circle. So here's my circle, and there's the diameter going through the center of the circle, and we mark it as D. We have a radius, and we call it R. You are all familiar with the relationship between the diameter of a circle and the radius, so we can write that as an equation. So this is our second way. The diameter is 2 times the radius. That's what twice means, 2 times. Now we're going to choose some values for R, calculate some values for D. So we do that and we tabulate the results in a table of values. Do we get to choose R? We say that R is the independent variable. So we start with R, we choose it, and I'm going to choose just the positive numbers. So I'm going to start with 1. 2 times 1 is 2, gives me the diameter D, which is 2. If R is 2, 2 times 2 gives me 4. If the radius is 3, then 2 times 3 is 6. And I'm not restricted to just whole numbers. I could choose 3.5, and then the radius would be 7. We say that R is the independent variable. We get to choose it. Here, we pick these values, but once we choose it, D, or the diameter, depends on the value R that we choose. In this case, the diameter is the dependent variable. This we calculate, and this we choose. So it's our start value. Remember, I did say that we are only allowing positive values for the radius. Also, I said we are allowing fractions, or decimal numbers. We could even have radius of a circle is the square root of 3, then the diameter would be 2 times the square root of 3. Here are some more terms for you to associate with the variables in a relation. R, in our example, is the radius of a circle. It is the independent variable because we get to choose it. Once we choose it, we apply our rule, multiply it by 2 to get the diameter. D then, our diameter, is the dependent variable, and we calculate it. So over here I've written our variable R is the independent variable. The domain R is a real number that is bigger than 0. We do not allow equal to 0. The diameter, D, is the dependent, and it has a range value. So you can think of range as up and down, mountain ranges, and D, it will also be an element of real numbers, but D will be strictly greater than 0. Another new term that you should know is the range. R, independent variable, and it has domain values. D is the dependent variable, and it results in different range values. I've summarized what we've done so far. So we've discussed a circle with the relationship the diameter is 2 times the radius. We write the equation as D equals 2 times R. Extracted the table of values here, and I've copied it down.
The fourth way to show a relationship is ordered pairs.
I can't list all possible ordered pairs for you, but I will pretend these are the only allowed values for my example. So, I would say it's the set of ordered pairs 1, 2, 2, 4, 3, 6, 3.5, 7, and root 3 to root 3. So this would be a set of ordered pairs for this table if these were the only values allowed for the radius. Okay, that's our fourth way. If we wanted to show all possible values, and we've just sampled these, then I could then use the fifth way to represent this relation, and that would be in the form of a graph. So my fifth way is a graph. And because I'm only dealing with positive values, I'm only going to work with the first quadrant. So I'm going to have the horizontal axis here, value, label it R as the radius, and D is the diameter. And I'm going to label the origin like this and put a circle around it because I'm not allowing 0 for the radius. And then I'm going to mark the values 1, 2, 3, 4, 5. And try to keep it regular, and of course I'm just doing a sketch. So let's graph our ordered pairs. First you go left and right. In this case I need to go right to 1, the radius 1, and then I go up to 2, 1, 2. Okay, forgot to mark my unit here. That's my first point. My second point is 2, 4, so I go over to the right to 2 and up 4. There it is. And I'm going to draw my line, and I'm hand drawing this. This is a sketch. Alright, and if I want to show that the graph goes forever, then I will draw an arrow at the end. I make the line solid to indicate that all numbers in between 1 and 2, in between 2 and 3, in fact, even between 0 and 1 are allowed. So everything along here is allowed. And we say that this is a continuous graph. There are no holes in it. It starts over here, but it's not a hole. If I said I'm only allowing whole numbers for the radius, in other words, I will not allow 3.5, and I will not allow irrational numbers like the square root of 3, just the natural numbers, 1, 2, 3, 4, 5, 6, then they become a discrete graph. So here it is. So here's a small sketch where we're only allowing discrete values. So if you graph this, 1, 2 would be here, 2, 4 would be here, 4, 3, 6 would be here, and these points would line up along a line, but I'm not allowing the line, only dots. This is called a discrete graph. Allowing the graph then is are points. Okay, so this is the graph. So of all the 7 ways listed, we've covered the sentence, the equation. We have a table of values, ordered pairs, a graph, and if you graphed it, if you allow all values for the radius, called a continuous graph. If we are restricting ourselves just to the natural numbers, 1, 2, 3, 4, 5, then we end up with a discrete graph. An arrow diagram is the 6th way of showing a relation. If I used our example again, even though it's not the best way to represent our example, we do 2 bubbles. One bubble contains all the values of the domain, or the independent variable, and in this case it's the value r, and we're going to calculate the diameter, which is 2 times the radius. And those values go into the second bubble. I'm just going to extract the values from the table. We had a 1 for the radius, then the diameter becomes 2, and we draw an arrow to it. The radius is 2, then the diameter is 4. If the radius is 3, it gets mapped to 6, and if the radius was 3.5, it gets mapped to 7, and if the radius was the square root of 3, the diameter is 2 times the square root of 3. So that is your arrow diagram. The domain values are here, and the range values are here. So these are the independent values, abbreviating here, and these are the dependent values. So the 7th and final way, we are going to use set notation. And notation means symbols. The curly brackets represent the set of. A vertical bar like this means such as. A backwards E like this, it means element or member of something, or we can also say that it belongs to. And I could not list all possible values here, nor could I list them all in a table. I got closer by graphing it, then I could draw a line to indicate all the many values that the diameter and the radius could have. How does this look in set notation? Yeah, the sentence, the diameter is twice the radius. Well, here it goes. It's the set of all ordered pairs RD such that the diameter is 2 times the radius. The radius is an element of the set of real numbers. The radius is greater than 0. And this is set notation for the diameter is twice the radius. The set of all ordered pairs RD so that or such that diameter is equal to 2 times the radius. The radius is an element or belongs to the set of real numbers, and R is greater than 0. When I use the symbol R, I mean the set of real numbers. And the set of real numbers are all the ones that you're familiar with. Let's go back to when you were little and you first learned to count. N is the set of natural numbers. The set of null numbers, 1, 2, 3, and so on. You started to count. Then you learned about 0. So then we introduced you to whole numbers. In addition to all the natural numbers, we include 0. 0, 1, 2, 3, and so on. When we introduced subtraction to you and you subtracted a big number from a small one, you ended up learning about integers. So we use I for integers, and it's the set that starts from negative infinity, goes to negative 2, negative 1, 0, 1, 2, and so on. This next one is going to be a little bit unusual. I'm going to use Q to represent the rational numbers. I'm going to use set notation. The rational numbers are the set of all numbers A over B such that A and B are integers, B cannot be 0. This is the formal definition of what a rational number is. Basically, it's a fraction, as long as this bottom number is not 0, because we cannot divide by 0. This is a division problem. The division problem results in a quotient, which is the answer to a division problem. So we use Q to represent the set of rational numbers. So there you have all the different ways to represent a relationship. Some are better than others to represent a particular relation. In this case, a table of values didn't express all possible values, the relation, and neither did ordered pairs. A graph was better for this one. An arrow diagram is not as good. Set notation. It's not used so much here, but it will be when you get into Pre-Calc 11 or Foundations of Math 11, and you will be using a lot of this if you take math courses at the university level. Be familiar with this, particularly if you are going to be continuing on to higher level mathematics courses.